I built this router table back in 2020. Every time I wanted to adjust the bit height, I had to watch the scale and turn the handle by hand. It worked, but honestly, it was pretty annoying. So this time, I decided to build an electronically controlled router lifter and have some fun with it. I spent several days designing the 3D model. This router lifter uses linear bearings to achieve both smooth vertical movement and rigidity. I also used a trapezoidal lead screw so the height can be positioned accurately. The overall structure is a gantry-style frame. By supporting both sides with vertical columns, the design is intended to maintain as much rigidity as possible. Using this 3D model, I started printing the parts with a 3D printer. For the filament, I chose a carbon fiber reinforced PET material, considering both rigidity and heat resistance. The total filament consumption was about 700 grams, so 1 kilogram of filament is more than enough to print all the parts. For areas that need more strength, I embedded nuts directly into the printed parts. Now all the printed parts are finished. Some of the parts need threaded inserts. To make the inserts hold more securely, I heat them up and press them in while melting the plastic. This jig was also made with a 3D printer. I showed it in more detail in a previous video, so please check that out if you are interested. While checking that the plastic is slowly melting, I press the threaded insert into place. This gold colored part is a trapezoidal lead screw nut. I fit it into the 3D printed part and secure it with tapping screws. Sets that include the shaft and bearings are sold relatively cheaply online. This is the linear bearing. It is used to create accurate linear motion. I press the linear bearing into the 3D printed part. The bearing holder has a slit structure, so it can be tightened firmly with screws. This is the bearing that supports the lead screw. The force from the lead screw is supported by this bearing. I secure it firmly with hex socket bolts. Next, I attach the columns to the plate. At the time of filming, this was still a prototype, so I only used screws. But if you actually build this, I recommend using adhesive as well. Using adhesive together with screws greatly improves rigidity. Now I insert the linear shafts. This is also just a prototype assembly, so they are only inserted for now. After the temporary assembly is finished, I recommend fixing them permanently with adhesive. Next, I install the moving unit onto the linear shafts. I applied lithium grease to the linear bearings before assembling them. Then I attach the motor mount and secure it firmly using both screws and adhesive. This is the lead screw. I also applied lithium grease to it before installing it. The bearing that holds the lead screw has a set screw. By tightening this screw firmly, the lead screw is locked in place. This is the stepper motor that drives the system. To protect the wire ends, I crimp pin terminals onto them. This prevents the wires from fraying and shorting, and also prevents the screw pressure from cutting the wires when they are attached to a terminal block. I also twist the motor wires together to help reduce noise. This is the stepper motor driver. I connect 12 volts DC as the power supply for driving the motor. The wires from the motor are connected to the A and B phases of the stepper motor driver. For the microcontroller, I decided to use an inexpensive and easy to find ESP32. First, I put it on the breadboard and tested it. This microcontroller has a USB connector, so you can power it and upload programs simply by connecting it directly to a computer. Here, I uploaded a simple test program that moves the motor depending on which switch is pressed. The test program worked correctly. Next, I attached the coupling to the motor. This coupling came with a lead screw, but as you can see, the hole is larger than the motor shaft. So I quickly made a spacer with a 3D printer as a temporary fix. Now it fits the shaft perfectly, so I tightened the screws firmly to secure it. Then I attached the motor to the router lifter body. I tightened the coupling screws firmly so it does not come loose. If you want to make it safer, I recommend applying thread locker to the screws. Since this was still a temporary assembly at the time of filming, I skipped the thread locker here. This is a reliable Omron micro switch. I fixed it to a 3D printed mount with screws. This switch is used to determine the machine origin of the router lifter. Without this switch, the router could crash into the frame and damage the machine. I tightened the screws firmly so the router does not slip down. Now the main body is complete. Next, I will build the controller for the lifter. The basic control system can be built with just a microcontroller. However, some of the I/O pins need external pull-up resistors. I also need a converter to step the 12-volt motor power down to 5 volts for the microcontroller. In addition, the motor driver input is designed for 5 volts, but the ESP32 outputs 3.3 volt signals, so I use transistors to make the signal input more stable. I also use an I2C logic level converter for the display. When all of these parts are installed, the universal PCB looks like this. I designed the controller case while considering visibility and ease of operation for the buttons and display. I also added a rotary encoder so it can be operated intuitively. Threaded inserts are heat set into the screw holes. By the way, I used matte black filament for the controller case. I think it gives the controller a calm and stylish look. The case was designed to match the universal PCB so the board fits perfectly. This DC jack is used as an expansion connector. Designing it with expansion in mind makes it much easier to add extra functions later. This is the cable that connects the controller to the motor driver. I used a flexible robot cable. For easier maintenance, I made it detachable with pin sockets instead of soldering it directly. This is an HT44780 compatible LCD, one of the easiest types to find online. I used one that comes with an I2C converter module. I fastened the 3D printed mount with screws. This area does not require much strength, so I did not use threaded inserts here. Instead, I screwed directly into the plastic. Then I apply instant adhesive to this part and glue it to the front panel of the case. The reason I made it this way is just a small design preference. The front and back sides of a 3D print have different surface textures and different gloss levels. If those textures are not consistent, it can look surprisingly strange when the part is finished. So I intentionally made it as a separate part so the visible surface would have a consistent texture. Next, I glue the tactile switches to the mount using instant adhesive. I install the keys into the panel and fix the mount that I made earlier. This is not a potentiometer, it is a rotary encoder. This knob was also made with a 3D printer. Now I connect the switches with wires. These are also all detachable using pin sockets. This makes small modifications and repairs much easier, and I think this design was the right choice. At first, I considered installing a built-in LiPo battery, but I decided it would just waste the battery, so this time I used an AC adapter as the power source. Finally, I installed the decorative panel and fixed it with screws. The controller is now complete. The motor driver and the controller both use the same 12-volt power supply, so the positive and negative lines are shared and connected to the adapter. PUL and DIR are the pulse and direction signals for controlling the motor. The home switch is connected with a pin socket. Now the lifter system is complete. Before using it, I press the home button to register the machine origin. When the button is pressed, the machine automatically performs the homing operation. As you can see, the switch is working correctly. The display shows the current position, the target position, and the movement step size. The step size can be changed using the buttons on the left. You can also hold down the 0.1mm button to switch to 0.01mm increments. After selecting the step size, pressing the up or down button moves the lifter by that amount. Now I will check the actual movement with the height gauge. First, I set the movement step to 1mm and check the motion. As expected, it moves accurately. This is much more accurate and repeatable than adjusting it by eye. Next, I move it in 0.1mm increments. After 10 clicks, it moved exactly 1mm. Next is the rotary encoder. When I rotate it, the target value increases or decreases. At this point, the machine itself does not move yet. When I press enter, it moves to the position specified by the target value. In other words, I can register the cutting position as a target value. If I hold the manual button while pressing the up or down button, I can freely move the position. While the manual button is held down, I can also fine-tune the position with the rotary encoder. Next, I will try the calibration sensor. I connect it to the expansion jack on the controller. Then I attach the alligator clip to the router bit. I place the brass plate on the tabletop. Then I hold down the calibration button on the controller. The router automatically moves upward, and the position where it touches the sensor is registered as the work 0 point. Now that the operation has been confirmed, I will install it into the router table and try using it. After installing the tabletop, I run the calibration again to register the 0 point. Here, I set the target height to 5mm and confirm it with the enter button. Holding down the enter button locks the controller. This prevents accidental movement if I accidentally touch the controller. Now let's actually cut something. Yes, it worked without any problems. When I checked the cutting depth, it was 5.04mm. It is 0.04mm deeper than the target, but the result is generally as designed. This error is probably caused by slight differences in the reaction timing of the calibration sensor and the stopping timing of the stepper motor. So I decided to add a correction value. I enter the setting mode and save the correction value as minus 0.04mm. Then I run the calibration again. Now the calibration includes the correction value. Let's test the cut again. This time, the depth is 4.99mm. Now the machine can cut with even higher accuracy. Since the router lifter is complete, I decided to modify it and have some more fun. First, I added metal braces to increase the rigidity. This should make it more resistant to diagonal vibration. Then, I attached a switch handle so the router can also be used by hand. I fix it firmly to the frame with bolts. It is a little large, but the larger base plate actually makes it more stable. I install a switch on the handle. When this switch is pressed, the router moves to the cutting depth that was set in advance. I also attached a mount so the controller can be used as part of the main body. The angle can be finely adjusted with screws. The arm switch plugs into the same expansion jack that was used for calibration. When the software is switched to hand router mode, this jack is recognized as the arm switch. After setting the work 0 point in advance, I set the target value to the cutting depth. While the switch is pressed, the router moves down to the target position. When the switch is released, the program automatically retracts it to -5 millimeters. Now, let's test it. For this test, I set the depth to 5 millimeters to check the accuracy. In real use, for example, even if you want to cut a 15 millimeter deep groove, you can simply change the value and cut it gradually, such as 3 millimeters at a time. This should greatly reduce the need to adjust a scale by hand or measure the depth with a thickness gauge every time. Checking the depth, it looks like it was cut accurately. If you found this jig interesting, I'm selling the microcontroller program and the 3D printer data. Please consider purchasing them and supporting the channel. I'll see you in the next video. Thank you for watching.